Remember that in our convention, tensile stresses and expansion strains are negative. So if you were to subject this metal alloy to tensile stresses, so it expands in this direction, it will go like that. And usually with metals, we know they're ductile, so you go through a ductility phase, and then they harden, and then eventually they break. This is for a metal. You could also do a very similar experiment, but with rock. And instead of a bar made out of metal, you make a bar made out of rock. And you could do the same experiment, but you will find out the rocks are usually very brittle. First of all, its tensile strength is not high, and second, they are brittle, so they don't have any ductile deformation. So this value over here, that would be what we call TS, the maximum stress that the rock can support in tensile conditions. Okay, but there is a problem with this. We do not do this type of experiments in the laboratory for rocks. And the reason is that it's kind of difficult to get a rock and machine a rod of rock out of it. It's not very, very practical. And even if you were to do that, let's say that now I have a long rod over here. In order to perform this test, I will either have to glue here the rock and pull it in this direction, which it is possible, but then you have to make sure that the strength of your glue is higher than the strength of your rock, otherwise it's just going to break at the glue, and that just, of course, that's not what we want, right? And the other way sometimes is to get, if you don't want to use any glues, to get a shape of rock in which you can use here something that goes in it, grabs it, and pulls in that direction. But also shaping a rock to a specific shape sometimes also is very difficult. And there is even a third option that probably here, instead of utilizing a glue, you could have grab it with some jaws, but then you're going to damage the rock as you grab it with the jaws, right? So it's really not practical. So instead of these kind of experiments, we do something else, which is called the Brazilian test. I don't know why it is called Brazilian, but it's called Brazilian. When I was doing my postdoc, I remember I had a colleague that she was Brazilian and she was running Brazilian tests. I think that was fun. So let's see. What is the Brazilian test? Well, the Brazilian test, what it's going to do is going to take advantage of the sample, which is going to be usually shorter than its diameter. So if this is D and this is L, D has to be larger than L, and we're going to load it along the diameter. The result of that is going to be that an element of rock inside the disk, by solving these equations, We're not going to do that, but somebody did it for us. Assuming that this is a solid, it's elastic, it's linear, it's isotropic, you can show that in this direction you have tensile stresses, while, as you might guess, in this direction you have compression stresses. And this rock is going to break. Let me make another one over here. This rock is going to break with a fracture starting in the middle whenever this tensile stress surpasses the value of tensile strength. So basically what we do is we apply let's call it a force here, F, and sometimes we measure deformation, but sometimes it's not needed because we don't get much out of it. But what we see over here is that load increases, reaches a peak, and with this maximum value, I get the value of tensile strain, which is similar to that one. And this one, if you solve the equations, we're going to call this one PV is equal to PV divided 5 times L, which is the length, times the radius. Yes?
Is that strain the strain of the length?
Or yeah, it's the strain along the diameter in this direction. So let's run one experiment. Okay? Yes?
I was just wondering what happens if the diameter is less than the length?
If the diameter is less than the length, then you start to have some other effects for which the equation that we wrote doesn't apply anymore. Okay? All right. So I'm running a test now. Okay? Let me get the camera. So now you're gonna be in charge of reading the value. Can you see there? Well, okay, it's 3.7, right? 3.6. Okay, I have put 3.6 pounds on this rock. How much do you think it's gonna take before it breaks? This is a Berea sandstone, similar to the one that you tested in the lab. 23 pounds? 800 pounds? 1500? 180. Okay, well, just, think about a number in your head and let's see what happens. Okay, I'm going to start to load it, okay? Okay, so I think with this one we can go to a maximum of 600 pounds. So, okay, it's already taking 60 pounds. It's already 100. Oh, I was supposed to use the camera. Okay, so it's taking now 120, 150. Started to get a little bit harder to crank here. 270, okay? 270 is now breaking. And don't make any noise because I like to hear the noise, okay? So 400, those of you that thought it will take less, 400. 500. All right. What was the maximum?
106.
No.
Oh.
Before, the highest number that you saw.
I think I missed it.
Okay. I'll check it later on the video, but now, and you can check the video later on. Now it's 100 pounds, but I think it got as far as about 500 pounds. Okay, so let's say 500 pounds. Can you use this equation to calculate the tensile strength? We know that the length is 1 inch and the radius is 0.5 inches. Okay, can you make that number and tell me what is tensile strength? First one that gives me the number gets extra points.
What's the radius again?
0.5 inches. And probably you can't see right now from if you're far away, but you will see later here on the video that the fracture is going straight from the bottom to the top. And that's actually what we expected. So this is a good experiment.
318.
318? Okay, that kind of makes sense. So then example, then TS is 500 pounds divided by 1 inch divided 0.5 inches,
318, oh yeah.
and that's equal to 318 psi. Okay. That's what we get, and I don't know if you guys got another number, but that seems reasonable to me. So tensile strength of the rock, 300 pounds per square inch. So that means that you could, in this rock, if you had a bar, you could hang 300 pounds from it, and it will still resist that. So probably the weight of 2 times my weight. That's what you could hang from 1 inch and see and still be able to support that stress. If you compare this with the tensile strength of metals, metals have a much higher tensile strength. Even in wood sometimes has a higher tensile strength. Okay, so we have one value here. And you're going to do something similar in the lab during the week. Okay, this is going to be a short lab. All right, so now let me ask you the following. I have another sample very similar to this one in my hands. Do you think I can break it with my hands? No. I have very strong fingers.
No, you can't.
I do rock climbing, and I get to. I don't know if you guys ever gone to AVP, but I do blacks. I do sometimes blues, which are yeah. So, do you think I can break these with my fingers?
What is it?
No, yes or no? It was 300 pounds right here.
Not much.
Okay.
Oh.
Let me show you. I can. You may think this is a stupid example, but it is not. It is not, because my entire point here is that tensile strength also depends on the direction in which you measure it, right? If I were to pull this rock in this direction, I'm not going to be able to break it. If I were to pull even this direction, I won't be able to break it in tension. But here, it's super easy. So you may think, why is that important? Well, it is very important because, for example, sometimes in subsurface we don't have most of the time a continuous nice rock as the one that we test in the laboratory. Sometimes you may go and drill a wellbore through an already fractured rock mass. And if you drill a wellbore in this region, and let's say your wellbore is there, and you're trying to predict what is the tensile strength in this location, that tensile strength in that location is going to be 0. And similar things are going to apply with hydraulic fractures. When you already have fractures, your fractures are going to be much easier to develop in regions which are already fractured. All right, guys, we'll take it from here on Wednesday.